So if we take a look at these expressions, we have the left-hand side. We can take a look at that and say this is really just a linear combination of those vectors. And same goes for down here, except they, for some reason, use different variables, x's and c's. In any case, we have linear independence if all those coefficients of those vectors are all equal to 0. And if you can find a couple of them that are not equal to 0, then they are not linearly independent, which is to say that they're dependent. And dependent, as it sounds like, would mean that, we can write one of those vectors as a linear combination of the other. Maybe we can write that down for dependence. Linearly dependent. You can write one of the vectors as a linear combination of some other vectors. All right, so linear independence means you can write one of the vectors as some other vector, and didn't say anything about if any of these vectors are 0, but we can take a look at some of those problems where if one of these vectors is equal to 0, then they're considered linearly dependent. All right, let's take a look at some examples. Let's grab the book and take a look at some examples. We did one or two examples yesterday or last time, whenever last time was. And so let's do a couple more to see. These exercises, number 11, 12, and all those has a variable h. So let's take a look at them, and then we'll also see if we can graph them to see if we can make sense out of them. Let's see. Let's do number 12 from 1.7. And the instructions were to find out the values for h to make this set linearly dependent. Okay. So to find h that it's dependent, we want to basically get this set up so that we have C1, 2 minus 4, 1, plus C2, minus 6, 7, 3, negative 3, plus C3, 8H4, so that it's equal to 0. And for the dependent, we want them to not all equal to 0. So we want non-zero values for C1, C2, and C3. So for us to do that, we need to, well, you can write this as a matrix. I was going to say maybe you could just take a look at it and see if you can guess some values. You think we could do that? Like maybe if C1 was equal to something and C2 was equal to something and C3 was equal to something. I don't know. I guess what I'm trying to say is that can we multiply C2 by something and multiply 2 by something and then -6 by something so that they would add up to 8 or -8 or something. You know what I mean? So let's do like a guess and check, I guess. -2. Multiply this by -1. C1 would be -1, and then C2 would be +1. So this would be -2 minus 6 is -8, right? And then if you let C3 be +1, that would make the top one equal to 0. And we can double check that with the bottom line. So C2 would be -1, C1 would be -1, so -1 plus -3 is -4, and you add that to 4, and then you would get 0. So then that means we have -1, that's the C1. I'm looking at the second row, the middle components here. -1 times -4 plus C1 is +1 times 7 plus C3 is +1 times H is equal to 0. So we want to solve for H so that we can have this to be dependent. So this is 4 plus 7 plus H is equal to 0. So H has to be equal to -11. All right. I just thought about doing that, but let's do this in a more systematic way. Remember, the more systematic way is for linear independence is to create a homogeneous differential, a homogeneous system of linear equations, and then solve for it to make sure that we have a non-trivial solution, right? So let's do it that way, and we'll say this equation ax is ax times, or the matrix A times the vector x is equal to the 0 vector, where these vectors that we're looking at, the vectors v1, v2 up to v1, v2, and v3 are column vectors of our matrix A. So we have 2 minus 4, 1, that's the first vector, minus 6, 7, minus 3, and then 8, h, and 4. And then let's see if we can row reduce or do whatever to see if we can make this into row echelon form. It looks like I can multiply the top by 1/2 and replace that row. So let's just take that first step to have our setup look nice without having to swap. I mean, we could have swapped rows too, I guess. But and thinking about using MATLAB for this, but there's an H, and MATLAB doesn't know what to do with like random variables. So since it does these things numerically, so we'll have to do this by hand. So now let's get rid of the -4 over here, and that would be 4 times row 1 added to row 2. So 4 times -3 is -12 added to +7 is -5, and then we have 16 added to H. And we're here, so we might as well take another step in our elementary row operations, and we'll multiply the first row by -1 and add it to row 3. So we can make this bottom element 0. So -1, so this is going to be 0, and then this is going to be 0. I think we've wiped everything out. We have ourselves a row echelon form, not reduced, but good enough. So what would make this? So it looks like we're going to have an infinite number of solutions, but we need one more thing to, well, do we need anything else? Oh, so this is set equal to 0. So we have a free variable in 3. And then it looks like we should be able to get x2, -5 times x2 plus this business times x3 is equal to 0. So we get x2 is equal to minus h plus 16. 16? Yeah. Over -5. We'll just cancel the negatives. x3. And then x1 is equal to minus +3 x2 minus 4 x3. So the free variable is x3, so we need to replace this x2. So x1 is going to equal to 3 times h plus 16 over 5 minus 4 x3. All right. So we're going to have issues with anything here in particular? Could h have been anything? We said h should be -11 here, right? So what if h was equal to -11? Would this work? Looks like it would work, right? So h equals -11 works for this. Could h be anything else? What if we let h equal to, I don't know, 0? Would that work? So if h was equal to 0, we would get, kind of depends on x3, right? So we'll let x3 equal to a number, and then, except 0. So if h was equal to 5, this will probably work. We're going to get a value. If h was equal to 7, it would probably work. We'll get a value. So it looks like h can equal to anything, right? So regardless of what h is, it looks like we're going to have a dependent set. So this is going to be a set of dependent vectors. Any questions? Are there any questions? Oh yeah, I did promise you guys what it's gonna look like. Let's see. So we have those vectors. What are those vectors? So for me to create vectors, I need a starting point and an ending point in this particular program. So we have 2, -4, and 1. So that's one vector. Let's get the other ones. The one is -6, 7, and whoops. 7 and -3. So these are two vectors. If we create this third vector, and let's let h equal to, what was the one we got? 11. Let's let h equal to 11 and see what happens. What do you think is going to happen while I'm punching this in? Any ideas? Any guesses? It's going to be on the same plane. We have these two vectors where we saw the pictures and they look like they're going in different directions. 11 or -11? And then if we draw this third vector, it's all on the same plane. Does it look like it's all on the same plane? It would make it easier, but then I'd have to do it. So I'll graph it using parametric form. Let's see, was it S and T? That was U and V. U times the first vector. This is our first vector. Plus V times the second vector. This is our second vector. And if we let U and V just range from 1, 0 to 1, this is what we would get, right? So this is a span of U and V for values that are just going to go between just going to go between 0 and 1. So it's really that parallelogram spanned by those two vectors. Now, if I want to extend that into more of a plane, I would add to this. So let's go to -1 to 2. So we can see a little bit more of the plane, and then we'll see that that vector, which was in blue, is actually on the plane. Okay. Now that's for h is equal to 11, but we're saying if we let h equal to anything, this should still be linearly dependent. So let's mess around with the different values of h and see what we get. Yeah. Well, for two vectors that are linearly independent, they would span a plane. And so if you have a third or even a fourth vector that are linearly dependent on the first two, then they're all going to be in the same plane. Now, if it's only one vector and then the other one could be collinear, or if you have three vectors in R4, R5 or something, then linear independence there doesn't mean coplanar anymore because it's not on the same plane. So we put -11 before. Let's put 0 and see what happens. Well, that doesn't look like it stayed on the plane, did it? No, wait, we need to extend it. So I can't tell because it's yeah, we can do it mathematically, but we're looking at the graph, so let's do it. Let's go to -5 to 5. Looks like it's on the plane. Yeah. So we're looking at the blue vector, right? Let's make the vector bigger. So the blue vector looks like it's on the plane. So that looks good. Let's try a different vector or a different value for h. We said any value for h, right? So let's pick a number. 3. Still on, right? Actually, we can make this anything we want. Let's have it range and value. So if we pick any value for h, at least the values that I have here go from 0 to 10. Let's make it go negative. So regardless of what value I pick, it looks like it'll remain on that plane. Well, I don't know what the best view of this would be. Okay, get the picture? Get it? Okay, let's see if we can dig out another problem from the homework set. Values of h, it says here, determined by inspection if it's linearly independent. Do we want to do inspection stuff? Without performing operations. Let's try to do one of these theoretical ones. True or false? Let's see if we can do several of these. Uh-oh, it's not going to fit in our page. Can you still see? All right, in each statement, either true in all cases or false for at least one example. If false, construct a specific example. Show statement is not always true. Yeah.
Fixed variable that it's impossible to have linear independence. They'd all have to be free.
Yeah. Yeah, because you get a free variable, then you're guaranteed at least one solution. Non-zero, non-trivial solution. All right, statement is true. Give a little justification. Okay. Let's see. If V1 through V4 in R4 and V3 is going to be equal to 2V1 plus V2, then the vectors are linearly dependent. So you have 4 vectors in R4, and they're saying that V3 is 2 times V1 plus V2. Then the set of all those 4 vectors are linearly independent or linearly dependent. Is this true or false? This is false, that they're dependent. So we don't, that's right, we don't know anything about V4. So what does that mean? So what are you saying? True or false? This statement is true. True means that we can find a linear combination of these things set equal to 0 where the coefficients are not all equal to 0. So it looks like if we have 1 times v1 plus 2 times v1 plus 1 times v2 plus negative 1 times v3, 0 times v4. So in the definition, they say that not all equal to 0, which allows us to say, well, we can let 1 or 2 of them equal to 0. That would be fine. So this would force this thing to equal to 0 because they said that v3 was equal to 2v2 plus v1. And so by the given condition here, this thing is going to give you the 0 vector already. Let's put a vector notation. And so v4 is not going to come into play, so let's just put 0 there. So this is dependent. Okay? Is that clear? Do you understand that? Is there a question that might come up? Is it so confusing that you can't even come up with a question? Hmm? Maybe. You mean let's do more problems? Okay. Number 34. We're still in R4. It says V3 is equal to 0 vector. Then is this linearly dependent? Linearly dependent. So if one of the vectors is equal to 0, what can you say about your set? It's what? So it's dependent. So this has to be true. So that means we can find a linear combination, right? V1 plus V2 plus V3 plus V4. And so we can find numbers for these blanks that are not all equal to 0. That would make this equal to 0, right? So V3 was equal to 0. Let's multiply that by 15. Pi squared over 6. Which one's 0? V3. So let's multiply it by any number we want. And then we'll put 0 for the rest of them. And then now we've found coefficients that are not all equal to 0 so that this whole thing is equal to 0. So that's dependent. Well, that's what, no, for this to be, we're not finding one example. We're just saying anything here. So we could have put x not equal to 0 and then x3. Yeah. So anyways, this over here, number 34, is a good, it's a good problem to note and say that if the vector 0 is in a set, then the set is automatically linearly dependent. Okay. So by the definition of dependent means you get coefficients not all equal to 0 that would make that thing equal to 0. So it's going to be dependent. All right, let's do another one. Number 35. So we have two vectors, v1 and v2 in R4, and v2 is not a scalar multiple of v1. Is this linearly independent? So we have two vectors in R4, and one of them is not a scalar multiple of the other. Then are those two vectors linearly independent? Well, let's assume that's not equal to 0. Yeah, that's true. So any two vectors that are not scalar multiples will be linearly independent. Okay, regardless of where you are, and you're in R, they gave an example in R4, you can be in R2, R3, R15, it would still be true. Okay, the only way two vectors can be linearly dependent is that one of them is a scalar multiple of the other. If they're not, then they are going to span. In fact, we can even state that they will span a 2D plane. And I'll put plane in quotes because we know of a plane in R3, but a plane in R4, it's hard to visualize. It's still a plane, but it's hard to visualize. Maybe you can visualize a plane if you're in R4. Yeah, anyways. You could certainly, yeah, you could think about that. Temperature, time, yeah. Yeah. Well, here we're only talking about two vectors in our set. So just those two vectors are linearly independent if they're not collinear, regardless of where you are, R2, R3, R4, R6. Yeah. But if you throw in more vectors, then you have to consider all of them as linearly independent or not, and then that would be a different story. Okay. All right. I think we can go on past this. Anything else we should do? Why? Because it looks hard. So number 38, V1, V2, V3, and V4 linearly independent vectors in R4, then the set is also linearly independent. Hint, they say look at this equation. So V1 through V4 linearly independent. That means that V1 times X1 plus X2 V2 plus X3 V3 plus X4 V4 equal to 0. Because they're independent, then the only way this is going to work is that all X1 and X2 and X3 and X4 are all equal to 0, right? If they're independent. So they're asking, what if we take one of the vectors out? So now let's just consider the vectors v1, v2, and v3. And we're going to set that equal to 0. Well, if these 4 vectors are linearly independent to begin with, and you take out one of those vectors, then the remaining 3 vectors will still be linearly independent. So this is equal to 0. If you take out, there's no contributions happening in v4, x4 times v4. And so the only way that this is going to continue to equal to 0 is that if all these x1, x2, and x3 are all equal to 0 also. So this would be a true statement. Look like they're all true, huh? Maybe you guys can come up with a false statement another time. All right, I think that's good. Let's move on. Look at this. What's this? Oh, this would be a good problem to do in MATLAB. It's a big vector. Let's see. Now you guys can think about that. Let's move on to our next topic. Our next topic is oh, do we have the? Oh, I don't know if I mentioned this theorem yet. Let's put this theorem down in our notes. Did I actually close my? So there's a theorem here. It says an index set v1 through vp of 2 or more vectors is linearly independent if and only if at least one of the vectors, this is dependent now, linearly dependent if at least one of the vectors is a linear combination of the others. In fact, if S is linearly dependent and v1 is not equal to 0, then you can find a vector in another position that's going to be a linear combination of the previous vectors that are before that. Okay. I'm just going to make up an easy one. Is that okay? So I think these 3 are linearly independent. I'm almost confident that they are. And then let's throw another vector that's going to be a linear combination. I'll pick an easy linear combination where I'll just add the first two vectors. So 1, 3, 7, and 9. I just added v1 and v2. Okay. So I have 4 vectors, and they happen to be in R4. And then these vectors are linearly dependent. Even if one of them is dependent on a couple of others, then it's a dependent set, yes. Yes. Okay. So on the one side, it says that they're dependent. So they're dependent, that means x1 times v1 plus x2 v2 plus x3 v3 plus x4 v4. Oh, I haven't been putting arrows on my vectors here. Let me put arrows on my vectors. Is equal to 0, where x1, x2, x3, and x4 are not all equal to 0. And that's a 0 scalar without a vector. So that's what dependent means. And if it's dependent, that means I can actually find non-zero values for some or all of these x's, right? So the way I have this set up, I can let x1 equal to 1. And I think we did this a little bit. x2 equal to 2. And I'll let x2 equal to 1, sorry. And x3 equal to 0. And x4 equal to -1. So we could do a matrix to solve for this, or you can do whatever else you want. But we can get non-zero x values for these coefficients so that they would, the linear combination would be equal to 0. Now on the other side, they say that we can write one of these vectors. There's a vector that's a linear combination of some other vectors. And so on the other side, vector v4, and I wrote this so that it looks like it's a linear combination, is equal to 1 times v1 plus 1 times v2. So v4 is a linear combination of 2 other vectors. Okay? So if you can show that one vector is a linear combination of some previous other vectors, then that's going to work out. So in this case, the j that they're mentioning in the theorem, j is equal to 4. And it's a linear combination of 2 other vectors that are previous that. Well, I was going to say the same thing, but I wrote it here already. It's a linear combination of some previous vectors. Doesn't have to include all of them, like v3 is equal to 0 in this case. But this is all they're saying. You run through the vectors, one of them by itself is linearly independent. If you get 2 vectors that are non-collinear, then those two vectors are linearly independent. If you take a third vector and that the third vector don't happen to be linearly independent from the other two, then you have a set of 3 linearly independent vectors. And then you keep going, and then at some point, if one of them is a linear combination of the others, then it's dependent, and then you can be done. All right, any questions about this theorem? So if you have a linearly dependent set, that means you can write one of those vectors as a linear combination of the other. Okay, we're going to switch gears now and go to the next section, section 1.8. And we've always looked at matrices as as tools to help us. We looked at matrices as tools to help us solve for systems of linear equations. And then now we're going to look at a matrix in a slightly different way, as slightly different applications. And we're going to look at them as what's called linear transformations. So let's start with a definition. And let's see if we can take a look at this definition and try to internalize it and see what we can find out about this transformation or function or mapping. We've dealt with functions before, and in calc or pre-calculus, you define the function formally. A function takes in an input and then gives a unique output. So it's the same thing here, except the functions that we're dealing with back in pre-calculus go from R to R. Just takes a real number and gives you another real number for an output. Like the squaring function, x squared, you put in a 1, you get a 2. No, you put in a 1, you get 1. You put in 2, you get 4. You put in -3, you get +9. So you get this input-output business. Now, transformation or a mapping can now go from any dimension to another any dimension. So we're not just restricted from R to R, but now we can go from any vector space to another vector space. Well, restricted, whatever that means. It may be, maybe not. So same rules for back in pre-calculus, your domain, zeros in the denominator and stuff like that. Here, let's read through this. A transformation or a function or a mapping. T is the name, kind of like we used to say F. Going from Rn to Rm. Notice the subscripts here, or the superscripts. This is a rule that assigns to each vector x in Rn, so that's the beginning part, that's your input, and then gives it a vector in Rm. So t of x is technically a vector in Rm. The set Rn is called the domain of t. That's where you're getting the inputs from in Rn. And then Rm is called the codomain. That means your outputs will be living somewhere in Rm. And that's called a codomain. So the notation Rn arrow Rm indicates the domain of T is Rn and the codomain is Rm. And then here they add some more stuff. For X in Rn, that's your input space, your domain, the vector T of X in Rm is called the image. an image of one particular vector, x, under the action of t. And then the set of all images, they'll call it t of x, is called the range of t. What? Yes, what? All right, let's see if we can make sense out of this. Let's start with what you know. Nothing. And I'll use my example. So instead of t, we'll call this f for the beginning. This is a function, and let's say the rule takes in, I'll use a slightly different notation that takes in the rule. For each value of x that you have, your output is going to be x squared. So this is also known as a squaring function, the parabola, blah, 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 whatever it's called. And so in this really simple example that you should already know of, we have our domain is going to be all real numbers. And the codomain is going to be all real numbers. The image of x, so let's find a particular value for x. Let x equal 5. Then the image of 5 under the function f is going to be, well, we'll call it f of 5. What's f of 5 in this case? Squares it, right? So that's 25. So the image of that is 5. So we got domain, codomain, image, and the range is going to be all the possible image values. So what's the range of f? What values can you have as an output? All the possible values you can have as an output? 0 to infinity, right? Including 0 to infinity. So your range will be 0 to infinity. So you can visualize this. I mean, we can visualize it using a graph, but graphs are going to be hard to come by when we start looking at things that are bigger than R3. So you can say that this is your domain. This is your codomain. And the mapping goes from R to R. So your f function goes from real numbers to a set of other real numbers. Your range Your range only includes 0 to infinity because you don't have any outputs that give you negative numbers under the squaring function. So so this is what you have. So you know about this information already, right? Does this part make sense? Yeah. It means all the possible outputs. And that's physical representation on the graph would be a little bit harder to describe here. Usually what we want to look at is we want to look at the parabola, right? Which is great. If you could see that, that's great. But then when we start going to higher dimensions, the whole idea of this might be more complicated. So it's better for us to just look at what's happening in a number line, your domain, to the codomain, another number line. All right, so let's take this up a level. And let's say we have a transformation T going from R2 to R2. And let's say this takes our x value. So we need a vector representation. Now I can call it the vector x, but let me specifically, explicitly write xy, or maybe x1, x2. I'll stick with xy. And let's say we're going to send this to another vector in R2. Let's do something to it. Let's keep the x the same, and let's drop the y. So this is a function or a mapping or a transformation from R2 to R2. Okay, so it's clear what the domain and codomains are. Maybe I should have done this in a different. Because the domain and codomain are given in this statement from one thing to another. And let's take a look at some examples of some possible images that we're going to get. And for images, we need the specific x value for your input. So give me a point in R2. 2, 5. Where's 2, 5 going to go? Let's actually write it like this. T, that's the name of the transformation of 2, 5. So when x is equal to 2 and y is equal to 5, what's the output? 2, 0. Right? So this is the image. This 2, 0 is the image of t. How's it go? The image of, so 2, 0 is the image of 2, 5 under the transformation t. Like what? Okay. It does kind of, but I want to think more of it like a function machine. The input-output business. You know, those function machines you used to draw back when you were in 3rd grade. Did you guys used to do this? You've probably seen function machines before, right? Google it. Oh, I'll Google it. Oh, wasting time. Okay, let's do this. So this is an image that we would get. So you put in 2, 5 into your function machine, you're going to get 2, 0 for your output. Let's do one more. Give me something to put into our function machine. 3, 6. What's our output? 3, 0. Okay. They would be in the image, yes. So the image is a set. They would be in the image of t. Also in the range. So the range is going to be, imagine you're throwing a dart, right? And you're, I don't know if this is a good analogy. You have a yeah. So they're in the image set. But R2 is the bigger set that doesn't get hit. So the codomain just tells you where the image lives. But the image is going to be all the things that get hit by something in the domain, and the codomain would be possibly the whole image, or the image can be all of the codomain, or it can possibly be just a portion of the codomain. It depends on what t is equal to. So, like in this case, the picture that I would have is that your t goes from R2 to R2, right? So you can have all these things over here. This is your domain, and this is your codomain. Your codomain is everything in R2. But let's figure out what your actual image is, the range. Let's figure out what your range is. Okay? So your range is everything that gets hit. So can you describe what your range would possibly be if I say you can put any x and any y into this function? What are your possible outputs? Yeah. Everything except the x-axis? Or everything on the x-axis? So your range would be your whole x-axis. Because it takes out the y values. For anything in here, it gets mapped to something on the x-axis. And none of these things up here will get hit by anything in your domain. Regardless of what you choose here, you're never going to hit anything up here. You're always going to be hitting everything. And so we would also, along with this graph, another thing that might help is that we tried to say 2 comma 5, 2 comma 5 goes to 2 comma 0. 3 comma 6 goes to 3 comma 0. And regardless of what you choose, it's always going to go on the x-axis. So that's your range. So that's a transformation. T is what? The range. So we could say range of t, or RNG usually, is equal to just the x-axis. So you can just say x comma 0, such that x is any real number, and then it has to be 0 for the y. This vertical bar is a symbol for such that. And then, you know, this little e, right? Epsilon, it's like is an element of. Okay. All right. What's this got to do with matrices? I don't know. What? Coefficients of what? What? Well, I don't know.
Do you even say that the codomain is R2 in this example? Because you just don't want dimensions?
Technically, you still have to say it's R2 because of the way the linear transformation is written. It supposedly lives in 2 dimensions, x and 0. But the range happens to be 1-dimensional, yeah, in this case. So, well, this is an example. Well, let's shift over. What's this got to do with matrices in linear algebra? I guess we're in a class called linear algebra, which means we should be looking at linear transformations. And so, without really defining what a linear transformation is, I can say that matrix multiplication, if you find the right matrix, is a linear transformation. If you have some other extra restrictions of linear transformations. I didn't quite see this in the notes in the book. I mean, so I guess we should briefly talk about what a linear transformation is. Well, why don't we define that later? Sorry. So we can use matrices for special transformations that are called linear transformations. And again, we'll define that later. But for the sake of time, let's take a look at this matrix 1, 0, 0, 0. I hope that's right. Yeah, sure. So let's take this matrix and let's do the matrix multiplication. So I think we had some x values that were 2, 5, and 3, 6 or something like that. Let's call that x1 and x2. They're vectors. And let's figure out what those are equal to. So ax1 is equal to 1, 0, 0, 0. And then we're going to multiply this by 2, 5. We know matrix multiplication already, right? Because we studied that. And matrix multiplication, one way to look at that is you take this row and then you take this column, and then you're going to dot it. So 2 times 1 times 2 and 0 times 5. And then you do the same thing. You take this row and take this column and then multiply it or dot it. You get 0. So that's what we got last time, right? In our other one. So let's do another one. Ax2 equal to 1, 0, 0, 0. And that's 3, 6. Our x2 is equal to 3, 6. So if we do this, apply this vector onto this matrix, we're going to get 3, 0, which is also what we got before. So in fact, we can be general. Ax or some random x vector and then when we do this matrix multiplication, we get the transformation that we're looking for. So we can say that for this particular linear transformation, T is equivalent to the matrix A. The linear transformation T is equivalent to our matrix A. Which means if we study the matrix, then we can study stuff about the linear transformation. Okay? So there might be questions like, how did I get 1, 0, 0, 1? And I don't know. Are there any other questions? So there's probably a lot of questions for you. Serious, what you got? What's the rule? So if we think about this as matrix multiplication, we have a 2 by 2, and what's this? A 2 by 1. Yeah, so your answer is going to be a 2 by 1, and these have to match. So we didn't formally talk about matrix multiplication. They did some sort of definition of matrix multiplication by splitting your matrix up into column vectors and then multiplying it by something else. And so the more formal definition of matrix multiplication will have to follow this particular rule where the inner numbers have to match, and then you would get the new dimensions of your matrix would be the outer dimensions. So that's how you get 2 by 1. Okay. All right, so we'll take a deeper dive into linear transformations, and so for our next class, we're going to cover sections 1.8 and 1.9. Oh, there's a new worksheet number 2 that's out. Maybe it's not out yet, but it will be out by today.